from Virginia Tech, and then he joined the PhD program here at UCSD in 2015. So he's been here for about 4.5 years. And he's worked on a lot of different things, as you'll see in his presentation. The central theme of his PhD has been interaction of flexible structures with fluids, both passive and active structures. So he's going to focus on this, I think, today in his presentation. And he also looked at a few other problems related to dispersion of particles, which he won't have much time to talk about today. So his work has resulted in 4 journal papers so far, 1+1 in review, and a couple more in preparation. So it's been a pleasure working with him for the last few years. If everything goes well today, Brato is going to be joining the Flatiron Institute as a research scientist to work with Mike Shelley, starting next quarter. So without further ado, Brato, the floor is yours. Okay. Oh, just a second, the format of the exam. So this is the public part of the exam. So Brato is going to present for about 45 to 50 minutes or so. If there are questions during the presentation, please try to keep them to yourself until the end, unless it's a very short clarifying question. Then we'll have an open question session for the audience. Then I'll ask the audience to leave, and the committee will ask their questions. So, go ahead.
So thanks a lot, David, for the introduction, and good afternoon, everyone. Thank you for being here. So like David mentioned, my research is essentially a collection of problems that involve broadly 2 topics. The first problem is transport of active and passive Brownian particles in porous media, and the other center topic is dynamics of flexible filaments in viscous flow, which is really the main focus of my research. So instead of telling you about all these problems in small APS style talk, I thought I would just talk about 2 problems, one about a passive and one about an active filament. I will tell you in a moment what they are. So this is the broad outline. I will start by telling you why it's interesting to study filaments in viscous flow. Then generally outline some of the tools that I'm going to use throughout the talk, discuss these 2 problems, and hopefully I will have just enough time to talk about a few other problems that I worked on, and then I will try to summarize. So filaments and fibers are actually quite ubiquitous in Stokes law. Think of complex fluids or non-Newtonian fluids. They're essentially suspension of long-chain polymer molecules, filaments, and fibers. If you apply a flow, this microstructure can rotate and deform, and this deformation generates additional stresses at the microscopic scale that manifest themselves as interesting rheological property at the macro scale. So if you're interested to understand bulk scale properties of this kind of fluids, then it's often interesting and important to go back at the micro scale and look at the dynamics of individual filaments. So here you see a wood pulp fiber that's particularly important for paper industry, and it's deforming and buckling in a simple shear flow. And this kind of deformation gives rise to shear thinning or normal stress difference, which results in non-Newtonian rheology. This is an example of dense bed-up fibers, and due to the deformation, they have a differential response depending on which direction the flow is coming from. The particle can bend differentially, and as a result, you can use this setup as a flow rectifier. Over here is a classic Stokes flow problem, where you see a suspension of fibers sedimenting under gravity. And due to a coupling between long-range hydrodynamic interaction and deformation, this results in a cascade of instabilities. So in all these examples, I'm calling the filaments or fibers as passive because their dynamics is purely a result of viscous and elastic stresses. On the other hand, you can have active filament system or active polymer systems, particularly relevant for a biophysics problem, where the dynamics is dictated by non-equilibrium processes. Over here is an example from microtubule. That's a biological polymer. You can find it in the cell cytoskeleton. And this is a cartoon of an active process, where you see a tiny machine called a molecular motor consuming chemical energy or ATP and walking on these filaments. And as they walk, they generate some forces that push these filaments to have directed motion. In this movie, you see actually a dense or a microtubule sliding on a dense bed of tensile motors, and they can occasionally get hooked, deform, and buckle. So dynamics in this case is intrinsically non-equilibrium because there is a continuous influx of energy. And apart from viscous and elastic stresses, it's also governed by these active non-equilibrium processes. What typical of active matter problem is that now if you gather a lot of these active agents together, you can observe collective or emergent phenomena. So in this movie, you see dense suspension of microtubules performing this large-scale coherent motion. What I would do is that I will treat both passive and active filament problems as fluid structure interaction problems in viscous flow. Okay. So I think I kind of mentioned, but all these problems are dominated by viscosity, where in the low Reynolds number regime, inertia is negligible. And in this limit of 0 Reynolds number, the governing equation simplifies considerably, and you have linear constant coefficient homogeneous PDEs, where V is the velocity, P is the pressure. These are the Stokes equation. So if you want to solve a problem with a particle in this kind of flow, then the velocity field at any point can be represented as convolutions on the surface of this particle, and these convolution integrals involve the Green's function for the velocity and the Green's function for the stress. what's really nice about this kind of integral representation is that Stokes' equation defines a three-dimensional bulk volume problem. By this formulation, you kind of cast it as a two-dimensional surface problem defined only on the surface of the particle. So you reduce the dimensionality of the problem by 1 at the cost of solving some singular integral equations. For the problems of our interest, the interesting particles are long, skinny objects, polymers, filaments, and fibers. The diameters of these objects are much smaller compared to the length, so there is a natural spawn parameter in the problem, that's an aspect ratio alpha. And in this case, you can actually go one step further and reduce the problem that's living on the surface to a problem defined only on the center line of this particle. And this asymptotic reduction is known as non-local standard body theory. It is kind of tedious, but I will give you the main result. So the standard body theory essentially provides you a relationship between the center line velocity, that's xt, and the force F exerted by these objects on fluid. This is done with respect to some background velocity u infinity, and this mapping involves two operators, lambda and k. So let me tell you about these operators. Take a very slender rod and pull it in viscous fluid, then the drag in the tangential direction is half the drag in the normal direction. So drag in Stokes fluid is anisotropic, and this anisotropy is accounted by this local operator lambda, which involves an asymptotic geometric parameter c. The non-local operator, that's called k, it's an integral operator, and it accounts for hydrodynamic interaction between different parts of the filaments, or gives you the self-induced velocity of the filament. And this forms the basis of all the theory and computations that I'm going to do in the rest of the talk. So with that, let me move on to the first part, where I'm going to talk about dynamics of passive filaments in compressional fluid. The model polymer for this section is an actin filament. Actin is a biopolymer. It can be found in the cell cytoskeleton, and they provide rigidity to the cell membrane. You take one of these individual filaments and try to bend it, then they resist it, and associated with that is a bending energy that goes as curvature squared, where kappa is a curvature and is proportional to the bending rigidity, that's B. Now the backbone of these filaments are subjected to thermal fluctuations at a length scale called the persistent length, denoted by LP over here, where thermal and bending energies are comparable. If the length of the polymer is much larger compared to the persistent length, as in the case of DNA molecules, then they tend to be entropic or try to remain in a coiled conformation. On the other hand, if the length is much smaller compared to the persistent length, as in the case of arterial flagella, then thermal fluctuations don't play an important role. For actin filaments, the length and the persistent length is roughly in the same order of magnitude. As a result, the dynamics is dictated by both thermal fluctuation and elasticity. I should also point out that these filaments are extremely thin, with 7 to 8 nanometers of diameter. So you can assume them to be inextensive. It's very hard to stress that. So let me first tell you about the experiments. These were performed by our collaborators at ESPCI in France. Over here you have a microfluidic hyperbolic geometry. There is a flow from left to right. And the channel is optimized in such a way that in the convergence section you have an uniform extension rate, in the divergence section you have a uniform compression rate along the central line. The filaments are fluorescently labeled, and let's play a movie and see what happens. So initially they are fluctuating, then they enter this convergent part where they get stretched out by the flow. Then they experience compressive viscous forces in the divergence section, and that leads to an Euler buckling instability, giving rise to this strongly deformed configuration. So first, again, we have suppression of fluctuation by extension, then there is compression, buckling, and this deformed configuration. Now, if you look at this conformation, or in the snapshots over below, you can see that there is loops and kinks. And this kind of loops and kinks are indicative of a three-dimensional helicoidal structure that's emerging in this problem. So I just want to take a moment now and step back and want to argue that coiling is actually generic. We've been observing simple shear flow for long wood pulp fibers, seen during manufacturing of wet spun silk fibers in hyperbolic geometries, and also seen in simulations of Brownian polymers in similar geometric setup. More recently, there are some studies looking at transport of polymers in three-dimensional turbulence, and there also you see this helicoidal structure emerging. So it's extremely robust, seen across various length scales, different flows, but there is no mechanistic understanding of why coiling is happening. And that's the question that I want to answer. So for the modeling, we think of these filaments as three-dimensional space curve that are parameterized by arc length S, and the center line is identified by a Lagrangian marker, that's X. The hydrodynamics is given by the standard body theory that I already mentioned, and here I'm making an approximation. I'm just retaining the local leading order and isotropic drag terms. F is the force exerted by this filament on the fluid, and it has two components, one Brownian, one elastic. For the elasticity, we are thinking of these filaments as inextensible Euler-Bernoulli beams, with bending rigidity B, the fourth derivative is typical of bending, and T is a Lagrange multiplier that enforces this constraint of inextensibility. You can think of this as a line tension. I won't go into the details of how to model Brownian forces, but they essentially obey fluctuation dissipation theorem of statistical mechanics, and the problem is accompanied by force and momentary boundary conditions at the end of this. Okay, for the background velocity, U infinity, we actually choose to do something very simple. We neglected this complicated hyperbolic geometry that I showed you in the experiments, and just approximated it as a simple two-dimensional planar stagnation point flow field where epsilon dot is a compression. So there are two dimensionless number that governs the dynamics. First is the ratio of the persistent length to the length, and this measures the amount of thermal fluctuations you have in your problem. So if this number is large, then the filaments are stiff. When this number is order 1, then there's a lot of shape perturbations coming from fluctuations. The main control parameter, however, in the problem is mu bar. It's called the elastoviscous number. It's a ratio of the time scale of bending relaxation to the time scale imposed by the flow. And I want you to think about this number as a force signal. So essentially, if this number is large, then there are strong hydrodynamic forces trying to cause Euler buckling. That's the best interpretation. I will skip the details of numerical method to show you a movie from my simulation. Over here, you'll see the filament conformation, and this will be the projection of the cross section. So you see the filament moves, it experiences compressive viscous forces, and that leads to buckling instantly. Right at the onset, the buckling is actually planar, but almost immediately you see this three-dimensional structure emerging. The coils develop, and then the whole structure gets compressed by the flow, and you have finally a 3D helical structure. This is a quantitative time resolved comparison between my simulation and the experiments, and we have a very good agreement. From the left to right, you are seeing progressive time snapshots, and from top to bottom, I'm increasing the strength of the flow. Okay. And I want you to focus on the last column, where you see this three-dimensional helical structure emerging. So if you look carefully, there are some features to note. First, the number of loops or number of turns around this helix actually increases with the strength of the flow. So you go from top to bottom, you see that there are more number of loops around the structure. These structures do not have any preferred chirality because there is rotational symmetry in the problem. However, you can have helical perversions, so it's points around the axis. So the chirality of these conformations can suddenly change. You can have a right-handed structure becoming left-handed and vice versa. And these perversions are identified by kinks on this projection that are indicated by these arrows. And finally, I just wanted to notice that in weak flow, particularly if you look at the first conformation, the conformations are not really three-dimensional helicoidal. They remain planar, right? And that's an observation that I would like to explain later on. Okay, so I have told you about morphologies of the filament, but let's now go back to this question of why coiling happens. And to answer that, I start with the linear stability analysis of the slender body 3D equation, and I'm now thinking of a non-Brownian filament, so there is only one control parameter in the problem. That's the mu bar, or the elastoviscous number, and that's the forcing term. So the base state of the problem is a straight elastic rod that's kept in the stagnation point flow. And associated with this base state is a parabolic tension profile that's shown over here. Now you turn the crank, you perturb the conformations in the in-plane and the out-plane direction. That's xy in the xz plane, hy and hz are small perturbations. You linearize the governing equation around this base state and use the onsets of normal modes. So phi y and phi z are the mode shapes. That's hy and hz for the perturbations hy and hz, and sigma is the associated rho. So all calculations done, we end up with two eigenvalue problems for the perturbations hy and hz, and that's shown over here, where sigma, the growth rate, is your eigenvalue, and L is the linear operator. It turns out that these two problems are completely decoupled from each other, and that's because the flow is purely two-dimensional. And as a result, each of these modes, phi y and phi z, have their own growth rates, that is sigma y and sigma z. Further, it can be shown if you just redefine one of these eigenvalue according to this transformation, then these two problems are rendered identical. And this points to two important conclusions about the eigenspectrum. First, for any given value of the control parameter mu bar, the eigenmodes in the in-plane and the out-plane problem, that's phi y and phi z, will be the same. That's the first conclusion. And the second, the eigenspectrum for the outer plane problem, that is sigma z, is shifted from the in-plane spectrum by unity. In particular, sigma z is equal to sigma y minus 1. And this is not a big surprise because the flow is purely planar. So you expect the in-plane perturbations to get forced more and expect them to grow faster compared to the out-plane perturbations. So you can solve this problem numerically, and this is the eigenspectrum for the in-plane problem, that's sigma y that I'm plotting over here. And let me re-emphasize that the eigenspectrum for the out-plane problem is exactly the same, it's just shifted by unity. Now as you increase your flow or control parameter, there's a critical value at which one of the eigenvalues become positive, and that's a pitchfork bifurcation or the onset of Euler buckling instability. And associated with this instability is this classical C-shaped buckling mode that you see over here. Now as you keep on increasing your flow strength or the control parameter, you excite higher order buckling modes that gives rise to this phase and so on and so forth conformation. what I'm doing over here is now I'm coloring the first two eigenvalues, that is sigma 1 and sigma 2 in red and blue, that because they grow much faster compared to the rest of the eigenspectrum. And linear stability then kind of tells you that the eigenmodes associated with the most dominant eigenvalue or the most unstable eigenvalue will dictate the emergent conformations. So it's kind of instructive with that we just look at these two eigenvalues, and that's what I'm doing over here. And I'm plotting just sigma 1 and sigma 2 as a function of mu 1. And again, there are a couple of features to note. First, for any value of this control parameter, the eigenmodes associated with sigma 1 and sigma 2 always appear in even and odd place. So what do I mean by that? If the eigenmode associated with sigma 1 is an even shape mode, like a C, then the eigenmode associated with sigma 2 would be an odd shape mode, like an S, and vice versa. The second thing to note is that the difference between these two eigenvalues, that is sigma 1 and sigma 2, that's plotted over here, goes to 0 in strong flows. So if you increase your mu bar, these two modes essentially grow simultaneously or have the almost same growth rates. These observations kind of hint us towards what's going on. And this is a hand wavy argument. Let me go through this. So essentially you have buckling, and that initiates this even and odd modes, but they have almost the same growth rate. So you cannot expect one mode to dominate over the other. As a result, these modes must interact with each other through post-buckling geometric nonlinearities. And maybe their interaction can lead to this helical structure. That's our intuition. And just to illustrate that, you have one even mode and one odd mode. The eigenvalues are closely placed. If you just take a linear combination, you get this helical structure already. So this is a bit hand wavy, and we wanted to make this a bit formal. And for that, we did a weakly nonlinear theory, which is kind of tedious, but I will just outline the broad steps. Okay. The starting point is again the standard part theory equations, but now we retain these geometric nonlinear terms that we were throwing away for the linear stability problem. You again perturb the conformations, Hy and H0 perturbations. Then you expand these perturbations on the basis of the eigenfunctions defined in the linear stability problem, with the coefficients of the expansion being time-dependent amplitudes. Then you can take a cue from linear stability and say that, well, the first two eigenmodes have the dominant eigenvalues, so you can restrict this sum or truncate this sum only to the first two modes, and that's what I'm doing over here. So phi1 and phi2 are the first two modes. That's one even and one odd, and A1, A2, A3, A4 are unknown amplitudes. Now you plug this expression over here, do some tedious algebra, massage them a bit, and essentially you have to use orthogonality of adjoint operators and adjoint eigenfunctions, but all things can be done, and you end up with ordinary differential equations for the amplitude in the spirit of Ginzburg-Landau equations. Now if you take a look at these ODEs, the first term is dA1 dt is equal to A1 sigma 1, and this simply means that the amplitude A1 grows exponentially fast with the growth rate of sigma 1, and that's purely the statement of linear stability. What the nonlinear terms do is that they couple these unstable modes or the adjacent modes and allow them to talk with each other. So this is a minimal representation of post-buckling nonlinear feedback that couples these modes. Now what we can do is that instead of solving these complicated PDEs, we can just solve these ODEs, and that's what I do over here. We plot the amplitude as a function of time, and over here I plot the filament conformation, and this is the projection. So let's take a look how this works. So you see there is buckling, the conformation remains planar, and then there is nonlinearity sticking in, and there is a spontaneous symmetry breaking that gives rise to this helical structure. So let's play that once more. That's planar buckling right at the onset. That's because the mode shapes are identical on this orthogonal place, but then the nonlinearities kick in, and that allows these adjacent modes to interact, and this is what is giving rise to this helical structure. So natural question is, how does it compare with full simulation? And that's the comparison. It compares really well. Over here, it's a full nonlinear simulation of this problem. First, again, you see this planar buckling conformation that's emerging, and then due to post-buckling geometric nonlinearities, you have this symmetry breaking and have the helical structure. What's nice is that in weak flows, the eigenvalues are well separated. As a result, one eigenmode can dictate over the other in the emerging conformation. And even though they interact in presence of nonlinearities, but these nonlinearities or nonlinear feedback are not sufficient to result in helical structure. So that's what you see over here. And that's precisely what was going on in the experiments. That's why in weak flows, you have planar conformations. Okay, so in summary, I've told you about why coiling happens, and that's because of interaction of unstable even and odd modes. And these interactions are encouraged because of this particular form of the eigenspectrum. It turns out that if you have any strain-dominated flow with a filament, then this eigenspectrum is quite robust. It's observed in many cases. That's why we see it is so ubiquitous and seen in so many cases. There are some other physical arguments that you can go for in favor of coiling, like it has a favorable energy landscape and so on and so forth. But I think I will skip that details. I'll just leave you with a movie where you see a non-grounding filament buckling in an axis-symmetric moves, and then there is this helical structure. Okay, so let me switch gears and now talk about the second problem. That's the dynamics of active filaments, and what's really inspired us to probe this problem is oscillations in ciliary flagella. So if you're not familiar, ciliary flagella are thin hair-like cellular projections. They are long, skinny, floppy objects and play a variety of crucial roles at the cellular scale whenever there is something to do with motion. So here's an example of a sperm cell that propagates bending waves along its flagella in order to swim. This is a green algae chlamydomonas performing breaststrokes with spare flagella for swimming. Cilia is typically shorter. They beat in an asymmetric beating pattern and can be found in dense arrays covering cell surfaces. And together they generate these beautiful waves called metachronal waves that can help in long-range fluid transport and also in swimming of single-cell organisms. So the first question that we are interested in is how do these things beat? And that's a question of active filament, because inside this structure, inside these floppy objects, there is a mechanism that consumes chemical energy or ATP. So there is an influx of energy, and that energy is then converted into mechanical motion that results in this spontaneous oscillation. So we want to understand what's the mechanism that results into these spontaneous oscillations. And the second question is related to, in some sense, emergent behavior, or particularly hydrodynamic interaction between pair filaments and this synchronization. So this problem has a very rich history and goes back to the pioneering work of G.I. Taylor in the 1950s. It all started from the observation that if there are two sperm cells that are swimming side by side, then their flagella can get phase locked and remain in phase. And more recently, over the last 2 decades actually, there are a lot of experiments with the algae chlamydomonas that have revealed that they have this pair of flagella that can beat in phase, resulting in breaststroke swimming, and also can go anti-phase, resulting in freestyle swimming. The long-standing hypothesis is that this kind of phase synchronization is due to hydrodynamic interaction between the pair of filaments. So we wanted to probe this question and understand what's the role of fluid structure interaction problems to dictate emergent behavior or phase synchronization of pair of filaments. Okay. So let's start with the first question of how do these things beat. So I told you cilia and flagella are these thin hair-like objects, slender filaments, and it turns out they have a very similar internal structure. It's called the axon. If you take a cross-section of the axon and put under electron microscope, you always see something of this sort, where there are 9 microtubule doublets arranged in a circular fashion. So I don't want you to get lost in jargons, but essentially microtubule doublets are just biological polymers, again thin, long objects. So if you look at the schematic, there are these 9 polymers arranged in this circular fashion, and they're connected with each other through what's called nexin links. These are protein links that provide structural integrity to the whole thing. I will do one step of coarse graining and ask you to focus on this cartoon over here. Here you see 2 microtubule doublets that are sitting side by side. And due to their molecular structure, there is a plus end and a minus end, so they have some polarity. These small red objects are molecular machines called dynein motors that sit on one microtubule, extend their arms, and grab the other microtubule. In presence of chemical energy or ATP, these machines try to walk towards the minus end of the filament, and as they move or walk, they generate forces that try to cause sliding into this filament and dissipate with this whole structure. So that's what you see right here. However, like I mentioned, these filaments are connected with each other through this spring-like structure, the nexin links. And as a result, this free sliding is prevented, and the sliding forces are converted into an internal bending moment that bends this whole structure in one direction. Now let's go back to this picture. These blue and green arms are representation of molecular motors, and they're arranged in such a way that the motors on 2 opposite sides of the cross-section operate antagonistically. In particular, when the blue motors are active, the green bond remains silent, and the whole structure bends in one direction. And once it has deformed, there is some geometric feedback from the structure that tells these blue ones to remain silent and these green ones then fire. And as a result, that changes the sign of the bending moment, and then the whole structure bends in the opposite direction. And that's how bends are generated by periodic switching, and this results in a spontaneous oscillation or traveling wave propagation of the filament. I just want you to appreciate that this process is extremely efficient because there are thousands of molecular motors that need to coordinate with each other. And also there are 50 or 100 times this switching is happening per section. So it's extremely efficient. What we want to do is that we want to build a simple structural model that retains some of these internal mechanics, internal details, and then prescribe geometric feedback coming from the deformation of the structure that can regulate the dynamics of these molecular motors and result in this periodic switching. So for the structural model, we coarse-grain this three-dimensional structure as a two-dimensional planar projection where the 9 multituple doublets are approximated by two polar filaments X plus and X minus that are clamped at the base, separated by a distance A, which is the diameter of the axle. And I'm interested in the dynamics of the central line, that's X. You can think of these polar filaments X plus and X minus being microtubules on two opposite sides of the cross-section on which the antagonistic operation of the molecular motors are superimposed. So like I mentioned, these motors try to cause sliding between the two filaments, and this results in an arc length mismatch known as the sliding displacement that's given over here. That's delta. It's simply the diameter of the accident times the tangent angle phi. And that's pure geometry. You can now compute the forces that these motors are generating. N plus and N minus are the fraction of bound motors on the filament X plus and X minus. Each of the motors apply a force of F plus and F minus, so that's the net force. And then you multiply this whole expression by rho, that's a density, line density of molecular motors, to get a force per unit length. And then there's a passive component that I mentioned before. So the next in links, which is this spring-like structure, that resists this free sliding, and that adds to this component of force to the leading order, which we model as linear springs of stiffness K. So this force is equal and opposite on each of these filaments, and that generates an internal active moment that goes into the moment balance equation, along with the passive component of the backbone that we model as polygonality. So for the kinetics of the molecular motors, we do something very simple. It's essentially a first order kinetics where the bound motor population can change by attachment and decrease by detachment. The attachment is proportional to the fraction of unbound motors at any instant with characteristic rate constant pi naught. And in experiments, it's known that the detachment rate is sensitive on loads or the force that these motors exert. In particular, the expression that I'm using suggests that if the loads or the force exerts a critical value, Fc, then they detach catastrophically or exponentially fast with the characteristic rate constant being epsilon naught. In order to close this model, we need some geometry, and that comes from the force-velocity relationship of molecular motors, and that's again something that's been measured in experiment. So that's the force-velocity relationship. All it tells is that when the molecular motors are not moving, when they're just sitting still, they can exert a force of F naught, that's called a stall force, and the load carrying capacity decreases, and it decreases linearly over a velocity scale V naught and goes to 0. So with that, you have this expression where there's feedbacks from the geometry that dictates a force, and that in turn dictates the population of molecules. So okay, so I want to pause here for a moment because the last two slides are very dense. It's just full with information. So I just want you to remember this big picture of this problem. Okay. You have a floppy object, like a filament, the cilia or flagella, and on this object there are these tiny machines or molecular motors sitting. These motors consume chemical energy or ATP, and with that energy they generate some forces. And through the internal structure, that forces is converted into some moment that bends this structure or deforms this whole structure, and you have a deformed geometry. And now here comes the most crucial part. The geometry then feeds back to the dynamics of the molecular motors. The geometry then dictates what are the number of motors that can be attached at any instant of time, and that in turn generates the forces. So the cause and effects are coupled with each other, and through this feedback loop, we can have a spontaneous oscillation. There is a lot of things that's going under the hood. I'm solving an integral differential equation that's coming from the non-local Chakrabarti theory, and coupled with that is a stochastic kinetics of molecular motors as well. That's not really important, but the main point is that I'm not pre-imposing anything, and everything is coming through this feedback. Everything is spontaneous. There are a lot of parameters in the problem, which you have to take my word for it, that can be estimated from experiments. There's no fitting parameters virtually. If you estimate all the parameters, non-dimensional is a governing equation, and you end up with 4 dimensional number, among which 2 are extremely important. The first one is called the sperm number. It measures the damping in your problem. So if this number is large, essentially you have large viscosity, and the problem is well damped, it's a lot of dissipation. And the second number is an activity number. It measures the ratio of the force scale generated by the molecular motors to the typical elastic forces. And this is, again, you can think of this as a forcing term, which measures, so if this number is large, essentially you have large number of molecular motors trying to deform this whole structure. That's the interpretation. So we'll vary these 2 parameters to see what kind of beating patterns or dynamics is possible in the system. Okay, so this is a typical phase chart. On the x-axis, I'm plotting sperm number. So as you go from left to right, I'm increasing the damping in the problem or the viscosity of the problem. On the y-axis, I'm plotting activity. So as you go from bottom to top, I'm increasing the active forces in the problem. For a given sperm number, as you keep on increasing activity, there is a critical value at which a hot bifurcation takes place, which you can predict through linear stability. And this bifurcation gives rise to traveling wave solution on these filaments that propagates from tip to base, as you see over there. And this behavior persists close to the bifurcation regime, that's in this pink regime. However, if you go really far from the bifurcation limit, the truly geometrically nonlinear region, then the direction of wave propagation changes, and then waves start propagating from west to tip, that you see over here. And this is the regime where you see biologically relevant oscillations. So, as you can clearly see that in weak sperm numbers, in small sperm numbers, the damping is small. As a result, you have these high amplitude oscillations. And in large sperm numbers, when there is more damping, the amplitude is small, but you have high wave number oscillations. I just want to make a passing comment that these waveforms actually compare extremely well quantitatively with experimental waveforms in terms of experiments and mode shapes and everything. This transition in the direction of wave propagation happens over through a small band of gray area where it's characterized by this kind of chaotic dynamics of standing waves. And again, let me re-emphasize the main point before I move on. Nothing is pre-imposed here. Everything is coming out naturally out of the problem. So the frequency and the waveforms are selected naturally from the parameters of the problem. So I've told you about sperm-like beating patterns, but you know that cilia have asymmetric beating patterns and chlamydomonas beating these breaststroke forms. So what about those? We can build those in an effective way in this model by some description where we propose the kinetics of the molecular motors to be biased, which means one group of motors have higher probability of attachment than the other. As a result, the structures are biased because bending on one direction compared to the other, and these biases break this illusion. For chlamydomonas, it's known from experiments that they have a static mode of deformation, which you can build in the model through a spontaneous curvature. And then you also need to tweak this detachment rate and make it depend on curvature, and that's again something that's been proposed in experiments. So we do that, not going into the details. And with that, we have these kind of waveforms. Here you can see cilia, it's broken in this left-right symmetry, you have these asymmetric waveforms that are emerging. There is a power stroke, there is a recovery stroke. And for chlamydomonas, you have this static mode of deformation, and on top of that, you have this wave propagation that results in this plunging motion or breaststroke pattern. Okay, so I've told you about different waveforms that's possible in the problem. Let's now think about the question of hydrodynamic synchronization or pair interaction. So to illustrate that, we have two active filaments that are placed side by side. And initially, as you can clearly see from this picture, they're anti-phase. That's the initial condition. And over here, I'm plotting the bound motor population on each of these filaments as a function of time. Again, you see these motors oscillating anti-phase initially, and that's not a big surprise because motors dictate the dynamics of a filament. So if the filaments are anti-phase, we expect the motors to oscillate anti-phase as well. Since there are numerical simulations, you can do funny stuff. And what I will do is that I'll let them oscillate without hydrodynamic interactions for a while. So you can see them oscillating anti-phase. And then I will turn on hydrodynamic interaction and see how things change. So you see them oscillating anti-phase, you see the motor populations also oscillating anti-phase. And then you turn on interactions, and almost instantaneously you see that the amplitude